Hi there. Today we're looking at pruning neural networks without any data by iteratively conserving synaptic flow by Hidenori Tanaka, Daniel Kunin, Daniel L.K. Yamins, and Surya Ganguly. So this paper on a high level does what the lottery ticket hypothesis does, but does so without any data. It prunes a neural network at the beginning, and it's able to do that because it claims that its algorithm avoids this problem called layer collapse, and then is based on conserving a quantity they call the synaptic flow. And we're going to look at this, and it's a pretty cool algorithm. It seems to work pretty well. As always, if you want to help out, you can share this video and let me know in the comments what you think of it. I do read the comments, and I would love to hear from you. All right, let's dive in. So they're saying pruning the parameters of deep neural networks has generated intense interest due to potential savings in time, memory, and energy, both during training and at test time. Recent works have identified through an expensive sequence of training and pruning cycles the existence of winning lottery tickets or sparse trainable subnetworks at initialization. So what is this paper talking about? If you don't know much about pruning, here is kind of a basic overview. So if you have a neural network that consists of many layers of neurons, what you can do, that one way of pruning that, what the goal is to end up with a small neural network that performs well. But for now, we have a big neural network that doesn't perform well. It hasn't been trained yet, right? So what you can do is you can first train the neural network, and then you have a big neural network that performs well, and then you can prune it. Now, a lot of the time, this has been seen as sort of the pruning way. You would train the big neural network and then you would prune it, because the other way was not feasible. First pruning and then training was not feasible. You might ask, okay, we might just want to start with a small one, and yeah, that's correct. So what does this first way buy you? This first way buys you mainly two things. So imagine this network right here is much smaller than the original network. So it uses less storage. So you can potentially, if you want to ship it to like a customer over the internet, you maybe, instead of a gigabyte, you only have to transfer a few megabytes. And that's pretty cool. The second thing, if you prune in the correct way, you can also make it faster, because now there's less weights to multiply with. You can actually make it go faster. So pruning is this combines with techniques called distillation and so on, are ways to make the networks smaller and faster. So if your customers are, for example, on mobile phones, then you can train a big network to a good performance on your big GPU server, and then ship it out to a mobile phone once it's small, and it will perform fairly well on that mobile phone without a GPU. So what about this other way? Now, in order to do the other way, we would sort of have to have an idea which one of these big networks, which sub-parts of these layers are the good ones, right? In order for us to do this first prune and then train. The interesting thing is that the lottery ticket hypothesis, I've done a video on this, and we've also interviewed the author on our ML Street Talk podcast. This paper has shown that this is in fact possible. A long time people have thought we need the big network in order to train, right? So sort of the bigness of the network, the full connectedness of the network is required for the training dynamics. But this paper has shown this is not possible. You can prune at the very beginning. Now what does it do? It first trains a neural network, like in the olden days. Then it prunes the neural network, and then it remembers which connections of the trained neural network it has pruned. And then it simply goes back to the beginning of training right here, up here, and says, I now know which connections are important, and I'm simply going to prune all the other connections other than these ones. And then, interestingly, if you prune first and then train, that works just as well and can actually work even better. The interesting thing here is that, I mean, this is a big cycle, but the interesting thing that the paper demonstrates is that this is even possible, right? People thought it wasn't possible, and this paper demonstrates if you only knew which ones you must retain, you can prune at the beginning of training. The lottery ticket hypothesis paper, though, still requires to actually train the full network and then do the pruning like in a classic way in order to find out which ones you need to prune and which ones you don't. This paper right here takes that idea and says, can we find a pruning algorithm that prunes at the beginning of training, yet does not have to train the full network. In fact, doesn't look at any of the data. Okay? And this is going to be our starting point. So their story is going to be, it's quite an involved story, and I think the overview is important as we go through the paper. So first, they name this problem called layer collapse. Now, layer collapse is going to be whenever a pruning algorithm removes the entirety of a neural network layer, which means that no information can flow anymore, and therefore the network can't train. And they claim that this is the main problem why these current pruning algorithms cannot achieve very high pruning ratios, so like very high compression ratios, is because they do premature layer collapse. They then formulate this maximal critical compression axiom that is sort of a guiding principle to build pruning algorithms. Second, they show that this quantity called synaptic saliency, a general class of gradient-based scores for pruning, is conserved at every hidden unit layer of a neural network. So they show that these are conserved, and they show this because this is their argument is going to be, first, their argument is layer collapse is a problem. The second argument is these things are conserved, and the conservation of the synaptic saliency leads to the layer collapse. And we're going to see how that happens. And then third, they say the solution to that is iterative pruning. So they show this at the example of iterative magnitude pruning, which we know avoids layer collapse. So iterative magnitude pruning is something that happens in this lottery ticket way of doing it. This lottery ticket way, you can actually do it not in one step, but it tends to work better when you want to go from 100% of your weights to just 5% of your weights. It tends to work better if you do it in stages. So first you go to 90%, to 80, to 70, and so on, down to your desired thing. And this iterative procedure, they claim, is what circumvents this problem of layer collapse. And then at last, they say we proved that a pruning algorithm avoids layer collapse entirely and satisfies blah, blah, blah if it uses iterative positive synaptic saliency scores. So they bring it all together and say, if an algorithm satisfies our axiom, and if the algorithm is an algorithm that uses these saliency scores, like this one here, and if the algorithm is iterative, then it is not going to be subject to layer collapse, and therefore it is going to be able to compress to a very high compression ratio. And then they actually do suggest an algorithm, this iterative synaptic flow pruning, SynFlow, that does all of this and never looks at any data. All right, this is quite a story. But remember what we're doing. First, layer collapse is a problem. Second, why is layer collapse a problem? It's because of this synaptic saliency conservation. Third, we can avoid it by doing iterative pruning. And lastly, this algorithm does it without looking at data. Okay, so layer collapse. Layer collapse is a pretty simple phenomenon. I've already said it. If you have a neural network and it has a bunch of layers, and let's draw a couple of neurons here, and the neurons are connected to each other via connections. And you have a pruning algorithm. Now, the pruning algorithms they consider here are so-called single-shot pruning algorithms. What they do is they look at the neural network, and this can be before training or after training, but at some point they look at the neural network, and they assign a score to each of these weights. Like they'll say, you're a 1, you're a 5, you're a 9, and so on. And then they simply prune away the lowest scores. Okay, and you tell the network what compression ratio you want. You tell the network, for example, please prune away 90% of the connections. So these algorithms would assign the scores once and then remove the bottom 90% of weights. Okay, like this. So those are the single-shot pruning algorithms. Now, what is layer collapse? Layer collapse is whenever an algorithm removes all of one layer. Because maybe, so here was a 9, maybe you have like 11s, 12, 13 here. Okay, so, and then you're in this situation right here, and the algorithm is pretty dumb. It's simply removing the bottom 90% of the connections, and here it figures I need to remove one more to meet that goal. I remove the one with the lowest score. I'm going to remove this one. And it's pretty obvious that now no more information can flow from the beginning to the end of the network because, well, where is it going to flow to? It's a bit more complex than that. Like, you can't just retain a layer, like a connection. For example, if this were a connection, there would also be no information flow because you'd have no outgoing connection here. But ultimately, layer collapse is whenever an entire layer is removed. Okay. And they do say somewhere that that's the case, I think. Layer collapse here. Layer collapse occurs when an algorithm prunes all parameters in a single weight layer, even when prunable parameters remain elsewhere in the network. So I'm not sure that this is like a giant problem. It gets to be a problem, but it could be circumvented fairly easily, right? By simply saying, if you're about to prune a connection that's integral to the information flow from the start to the end, don't prune that connection, prune some other connection, right? And then you could simply avoid that. And I'd be interested in how that works out. So, but in this case, for purposes of this paper, they simply consider algorithms that assign a score and then prune the bottom couple of percent, okay? So we don't want any like handcrafted rules in here or something. So they look at this quantity called the max compression. The max compression is a quantity that's basically the maximum achievable compression while still avoiding layer collapse. And they say, for example, for a network with L layers and N parameters, the max compression is N over L, which it basically means every layer only has one parameter remaining, and therefore, and if it's the correct one, therefore information can flow from start to the end. All right, so this is the maximum achievable compression. Anything beyond that would automatically induce layer collapse. Now, anything before that could induce layer collapse, but there is a way to compress the network to the same level without inducing layer collapse. And their point is basically that these other compression algorithms that they compare with, they always induce layer collapse before they actually have to, because they cut off a connection that leads to layer collapse before there would be another connection that they could cut off that would not lead to layer collapse. And of course, if you have done a layer collapse, then your accuracy immediately drops to 0 or to random, right? Because no more information flow. So they look at these things here. Random pruning is where you simply assign a random score to each connection. Magnitude pruning is what the lottery ticket hypothesis does, but just they look here at a single shot. So you simply look at the magnitude of the weights, and this can be before or after training. I think they do it after training here, which is classically done. You look at the magnitude of the weights and you prune the bottom 90% away. There are also two more advanced methods, these SNIP and the GRASP, so snip and grasp, which look at the gradient of the training loss in the network, and they decide according to that gradient which things to cut and which things not to cut away. The grasp even involves the Hessian right here. So they're fairly, complex method that have some thought behind them about why they do what they do, yet they all induce layer collapse before they actually have to. So they define this thing here called the critical compression. The critical compression is the maximal compression ratio a given algorithm can achieve without inducing layer collapse. So the critical compression here is basically whenever that algorithm goes to 0. That's the critical compression. That's kind of the farthest you can push the algorithm without German speaker, without it inducing layer collapse. Okay, so you can see that for these baseline algorithms, the layer collapse occurs way below the theoretically possible max compression. And we're going to see that in their algorithm, this SynFlow, that this max compression is achieved. And it's actually achieved without any of these handcrafted rules that I mentioned. It is the algorithm by design already achieves this maximum compression ratio. So they formulate this here as a guiding principle. They formulate it as an axiom. I would rather say it's like this kind of a guiding principle of building these algorithms, that any algorithm you build should have, so the critical compression ratio of a pruning algorithm applied to a network should always equal the max compression of that network. It basically means when you build a pruning algorithm, if you push that pruning algorithm to its limits, it should not do layer collapse unless it absolutely needs to. Okay? Again, the extent of this problem, I don't know, but they do demonstrate that that they can push their algorithm a fair bit further. Now, without inducing layer collapse, you already see that these other algorithms, like in this regime, apparently layer collapse hasn't happened yet because they still have sizable accuracy, but there's still there's a reasonable difference here between those and the SynFlow algorithm. So I'm not too convinced yet that layer collapse as such is the problem, because they have a difference before they're layer collapsing, as you can see right here. And I have the feeling that this difference here is due to this iterative procedure and not actually due to the phenomenon of layer collapse. But yeah, so if it were only layer collapse, what you'll see is that they do the same, and then at some point it's like, boom, now I have layer collapse. Okay. Yeah, so the layer collapse story, I'm not sure, but it's part of the story. So let's go with that. The second part, which is kind of disconnected. So they established two things. They established the layer collapse problem, and now they establish the synaptic saliency, which then later they're going to connect to the layer collapse. So the synaptic saliency, they say, is any score metric that can be expressed as the Hadamard product of this thing with the parameters. Okay, so each parameter is going to be multiplied by the gradient of some function with respect to that parameter. They say where R is a scalar loss function of the output of a feed-forward neural network parameterized by theta. Okay, so many of these pruning algorithms can be formulated in this framework right here, and their algorithm can also be formulated in this framework. So you can see the score that the algorithm assigns to a weight can be defined as such. And as I said, many fall into this category or are similar to this. Especially, for example, they say when R is the training loss L. So this is the simplest case. You put data through the network, and then you take the training loss of that data and you sort of backpropagate it. And now you're going to prune these connections according to how big the gradient is. If you say the gradient is very big, that must mean the connection is very important. because there's lots of information flowing through it. So if it's the training loss L, the resulting synaptic saliency metric is equivalent to the score metric used in skeletonization, one of the first network pruning algorithms. The resulting metric is also closely related to this right here. Now this, you can see it's not exactly the same, but it's closely related to the one used in this SNP baseline, and also closely related to this thing right here used in GRASP, where it's not just the gradient, it's actually the gradient multiplied by the Hessian to account for curvature. Okay, so they're going to investigate this synaptic saliency in neural networks. They formulate two theorems right here about the conservation of synaptic saliency. Remember, synaptic saliency is any score that respects this, that is built like this, any score S. The conservation of synaptic saliency. All synaptic saliency metrics respect two surprising conservation laws that hold at any initialization and step in training. So these are not usually like in distribution or something like this with high probability. These things hold at any point in the neural network. First is the neuron-wise conservation of synaptic saliency. For a feed-forward neural network with homogeneous activation functions, and a homogeneous activation function is an activation function that can be expressed like this. For example, ReLUs fall into that category. The sum of the synaptic saliency for the incoming parameters is to a hidden neuron is equal to the sum of the synaptic saliency for the outgoing parameters from the hidden neuron. So what does it mean? It's actually pretty simple. If you have a hidden neuron and you look at all the incoming weights and you look at their synaptic saliency, which is this S score of each of these weights, like what would the pruning algorithm assign to that, and you look at the outgoing ones, then the sum of all the incoming ones is going to be equal to the sum of all the outgoing ones. So that's pretty interesting. And they extend that to the entire network. So an extension of that, network-wise conservation of synaptic saliency. The sum of the synaptic saliency across any set of parameters that exactly separates the input neurons from the output neurons of a feed-forward neural network with homogeneous activation functions equals that. So it basically says it remains equal. So what does it mean? What does it mean to exactly separate the input from the output? That's basically the definition of a layer in a neural network. So what they're saying is that you have a bunch of layers, and if you look at a particular layer, like this one here, and you look at the incoming connections, and you sum up all of their synaptic saliencies, that's going to be equal to the sum of all the synaptic saliencies of the outgoing connections of that layer. And it can also apply to like a group of layers and so on, but the synaptic saliency is conserved in that way. Now, why is that important? And here is where we make the connection with the layer, layer drop, layer, whatever. Okay, the fact that these algorithms tend to drop entire layers before they have to. If you have in your network layers that are of different sizes, so you have large layers and then smaller layers and smaller layers, what will happen is that since the synaptic saliency is conserved, the sum is conserved, if you have more connections in one layer, so lots of connections, and in the small layers you don't have as many connections, the sum is equal. So that means each individual one here is much, much smaller. So the S is very small for each individual one here, and the S is very large in there. That means the pruning algorithm is going to really, really kill off these connections in the big layers, right? And it's actually going to kill them off to a point where it probably is going to eliminate that layer before it even prunes many of the connections of the small layer, right? Just because of that conservation fact. And they do experiments like this. I think there's an experiment up here where I like this one down here better, where they basically show that you have inverse layer size on the bottom, and you have the average score that the pruning algorithm assigns to any connection. Now, these, as we've seen, they're not exactly assigning the scores of this saliency, but they're very close to it. The SynFlow algorithm does exactly assign the synaptic saliency as the score for the pruning. Now, we've basically seen that this leads to a bad result, but the synaptic flow is going to compensate for that. But in essence, as you can see, as the layers get, so inverse layer size grows, which means that layer size shrinks. As the layer size gets smaller, the average score of the connections in the layer is higher and higher, which basically means that the pruning algorithm, if you just let it go by itself, it's going to kill off the larger layers first, because they have the smaller scores. And you can see that even though the other algorithms don't conform exactly to that, they conform to this approximately. So these here, because their score is closely related to what the SynFlow does, and the magnitude pruning, mostly because now I'm not sure if that's at the end of the training. At the beginning of the training, if you just initialize, then the score is going to be proportional to their magnitude, and their magnitude is determined by the initialization scheme, and the initialization scheme is most of the time, like modern initialization schemes, compensate for the fact that you have different number of incoming and outgoing connections, and therefore they would automatically assign a higher initialization constant to layers that have a lower number of parameters. So even the magnitude pruning will conform to this. Now, it might be absolutely reasonable to say that that's also the case at the end of training, because most parameters aren't going to move super much during training. So this still approximately holds, as you can see here. Of course, the random one doesn't do that. Yet, because you prune randomly, you're still absolutely subject to this layer collapse. In fact, in the random one, the smallest layers would be the ones to go away first, because it's just more probable. Okay. So we've discovered that if you do something like saliency scoring or something that's correlated to it, then you're going to remove the biggest layers first. And that's a problem. And that's what they say. This fact of this conservation laws and the single-shot nature of these algorithms, that they only assign scores once and then they prune away whatever the bottom such and such percent are, leads to layer collapse. Right? I think we've established this now, that the combination of the two things leads to layer collapse. Now they make a little bit of an excursion, and they say there is actually something that doesn't run into layer collapse, and that's iterative pruning algorithms. So specifically, they look at magnitude pruning. They say magnitude pruning, which, remember, is also, if you do it single shot, it also runs into layer collapse. Magnitude pruning avoids layer collapse with conservation and iteration. So because it iterates, it avoids that. And that's what these lottery ticket hypothesis paper does. It does it iteratively. It removes a couple of connections, then it retrains the network, basically recomputes the magnitudes and therefore recomputes the scores, and then it prunes again. And then it recomputes and prunes again. And by recomputing, you can basically, some of the connections that weren't important before but just survived the pruning, they can now be like, wait, I have now way more responsibility as a connection, and they will shoot up in importance to avoid being pruned. So you can see, if you push your network to a high compression ratio, then if you just do this single shot pruning, you run into this layer collapse. At some compression ratio, you simply crash to random performance or zero performance. Yet, if you do multiple iterations, you can see here already 2 iterations, then it's much longer before you run right here into layer collapse. And if you do 3 iterations, you do much more. Now the 3 iterations doesn't mean you prune more. Like at this point right here, to 10 to the 1, all of these things prune 9 out of every 10 connections. It's just the thing that has 3 iterations prunes maybe first 3 and then again 3 and then again 3 out of the 10. Whereas the 1 iteration would prune all of the 9 in one go. Okay? And they give a reason for this. They say that it's the fact that gradient descent encourages conservation. So they give a little toy example here. They say to better understand the dynamics of the IMP algorithm during training, a little smaller, we will consider a differentiable score, this one. So this is not exactly magnitude pruning, but it is very close, right? The squared, it's just the square of the parameter instead of the absolute value of the parameter. They say it's algorithmically equivalent to magnitude score. Consider these scores throughout training with gradient descent on a loss function using an infinitesimal step. In this setting, the temporal derivative of the parameters is equivalent to that, and thus the temporal derivative of the score is this. So now they're going to look at how does the score evolve when they train the network. And the score evolves exactly as the negative to the saliency. Surprisingly, this is a form of synaptic saliency, and thus the neuron-wise and layer-wise conservation laws from section 4 apply. In particular, this implies that for any 2 layers of a simple, fully connected network, then this quantity holds. So this is not new, but what it basically says is that through training, these connections equalize the saliency again. So if you have a very big layer, and here a very, very small layer, and because it's a big layer, these scores are very much lower, right? It's just little s, and here it's big S per layer. But then if you prune away and you run gradient descent on this, these scores will tend to become bigger. And in this case, these weights will tend to grow in magnitude. Because you've pruned away the others, they now have more signal probably flowing to them and more gradient flowing to them, and therefore they're going to grow in size, and therefore their score is going to be bigger. So this gradient descent of this iterative procedure makes the scores better for that. So basically counteracts the layer collapse. So they put all of this together and say, Theorem 3, iterative positive conservative scoring achieves maximal critical compression. If a pruning algorithm with global masking, and global masking means that you rank all of the connections and then prune from all of the connections. It's the difference to layer-wise masking, where you say, I want to remove 90% of each layer, which sounds like it would avoid layer collapse, but also it works a lot worse than the global one, the global strategy. Assigns positive scores that respect layer-wise conservation. And if the algorithm, so respecting layer-wise conservation, it basically means your score should be, or if your score is a saliency score, then that's the case. And if the algorithm re-evaluates the scores every time a parameter is pruned, then the algorithm satisfies the maximal critical compression axiom. Okay, so that's basically saying that if you have any algorithm that prunes with a saliency score, like theirs is going to do, is going to be able to be pushed to the limit until the maximal capacity is reached if you re-evaluate the scores every time a parameter is pruned. So this is basically saying that whatever the lottery ticket hypothesis paper did with magnitude pruning, if you do it with saliency-based pruning, you're guaranteed to achieve the maximum possible compression if you push it. But of course, we know that whatever the lottery ticket hypothesis paper did is impractical because it needs to retrain the network every single time it wants to prune, right? So if you want to do this after every parameter, that's going to be a long time. It's going to be impractical. We ideally want to prune the network before we even look at any data. And they're going to do exactly that with the SynFlow algorithm. They say theorem 3 directly motivates the design of our novel pruning algorithm, SynFlow, that provably reaches maximal critical... Oh no. Okay, this was bad. Maximal critical compression. First, the necessity for iterative score evaluation discourages algorithms that involve backpropagation on batches of data and instead motivates the development of an efficient data-independent scoring procedure. Second, positivity and conservation motivates the construction of a loss function that yields positive synaptic saliency scores. We combine these insights and introduce a new loss function where the one is the all one vectors, so yada, 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 yada. Okay, so this is the loss function of their saliency scores. And this might seem like, so what do we have? We have the parameters of layer L, the absolute the absolute value of those parameters, and then you simply multiply all of the layers together. And you have this product here with the ones on the side. So this is a quadratic form, sort of. Okay, this might seem a bit weird, but in practice, and this is also what happens in their code, you can do something pretty easy. So first, you have to transform all your weights to their absolute values. Now in their code, you can look at it. They do remember the signs for later. But first, you convert all of them to their absolute values. Then second, you simply take a data point that is filled with ones, that literally the number 1. So if your input is an image, you just put a 1 at each pixel. You feed it through the network with all of these positive weights, and you get out some output. You get some output vector, okay? Then you simply, you need to do this inner product with the 1 vector, which is simply a sum, right? I don't get why it's a bit of a funky way of writing a sum, right? You simply sum that up to get a single number. And this single number now is your pseudo loss function, right? It's simply the loss function that an all one data point gets when the loss function is just the sum of the outputs. That's it. And then you backpropagate that loss to the layers, right? So this is R. Remember, this is not the score itself, but our score is going to be the derivative of R with respect to a weight times that weight, okay? So you want to backpropagate, and then you multiply each of these weights by the backpropagated signal. And that's going to be your score for each parameter. Now this doesn't seem too hard, right? You don't even need a batch. You need a single data point, 1 backpropagation, and then you get your scores. Okay? You don't need expensive training or anything like this. This seems pretty cool. And they give an example here. For example, for a simple fully connected network, i.e. this, so they consider here a linear network, right? Just so we can look at exactly what happens. For linear networks, you can often compute quantities exactly. So if we look at just a linear network without nonlinearities, we can factor the synaptic flow score for any parameter as such. So the score this is now not the R, this is going to be the score is going to be this thing right here. So you can see that the parameter is multiplied by this thing and by this thing. And other than, for example, magnitude pruning, this actually takes into account all the input flow, because it goes from this one, it goes from this one, it goes through all the network, right? Every path that arrives at this particular weight is going to be considered, and every path that goes out from this particular weight is going to be considered. And the saliency score is going to depend on all of these paths, all of the information flow from input to output that goes through that weight. And if you do this, then you get a really good pruning algorithm. So yeah, the algorithm is I've already described it. And in their experiments, as you can see right now, they have a bunch of networks, these VGG networks or like wide ResNet. They have a bunch of datasets like Tiny ImageNet or C410, where they experiment with these different baselines. And you can see that the baselines often run into this layer collapse problem. Often run into this, where all of a sudden, let's look at this ResNet 18 right here. Maybe you can find a connection between, maybe there's differently sized layers in ResNet 18, and that's why the collapse happens even earlier. But you can see right here, there's a collapse if you do magnitude pruning. Even also if you do random pruning, it falls down pretty hard after a while. The baselines, they hold up better, but you can see in different models and different data sets that the baselines crash at some point as well. Now, I've already said the comparison here, it seems a little bit unfair. I might have overread something, but I'm pretty sure that the baselines remain single shot, while the SynFlow algorithm here is now, of course, no longer a single shot. It's actually multi-shot. And they've made the exact argument that the single shot is the problem, and therefore their algorithm is multi-shot. And it seems like they should give the other algorithms the opportunity to also do multi-shot, just to compare them fairly. Maybe, as I said, maybe they're doing that, but I haven't read anything. So it just seems like the comparison is a bit unfair if you identify the problem and then just leave the other algorithms with the problem. SynFlow is still different from these other algorithms, even if they had the multiple steps. Now, the counter argument to this, of course, is that these other algorithms all require the training data. They require actually passing the data or training the network in the case of magnitude pruning and so on. So that's pretty expensive, whereas SynFlow, you simply pass forward one data point and that's it. That's a good argument, but it seems like the effect of the synaptic saliency scores and the effect of the multiple steps aren't really disentangled in these experiments right here. It simply shows that it consistently outperforms other pruning methods. And what I'd like to see is really where that outperforming comes from. Okay, so that's what I think of this. And that was the paper, basically. I'm even if I am not convinced quite yet, this is pretty cool, right? And I think this will, if it's not used itself, it will inspire kind of a line of work into pruning at the beginning of training without looking at data. And maybe we can even think of building networks, like instead of just pruning them, we can think of constructively building networks that observe these properties, and therefore we can just construct initialized networks already with good properties, such that we don't even have to go to a bigger network and then prune it down. It seems wasteful. It seems like we should just be able to derive principles of what we want in how the weights are structured, and then construct networks that are according to that. And I guess that's what's going to happen in a few papers that are coming. All right, again, if you like this video, consider subscribing, giving it a like, commenting, let me know what you think. And until next time, bye-bye.